There we go. Lights. Okay, we're good. We're good. We're good. We're good. All right. What's up, guys? Kristen Edgy here. We're good. We're good. All right. All right. I'm looking at myself on the TV. Yeah. All right. So looks like everything's coming out clear. Everything sounds right. Uh, we go. I'm gonna do something a little bit differently. I'm gonna have the stream on my other iPad, so I can monitor what's going on here. Hold on a second. Give me, yeah. Okay, there we go. There we go. All right, great, awesome. All right, so what's up, guys? It's Kristen Ninja here. Welcome back to study sessions. Today we're finishing up that 462 review that I started yesterday. Um, I know some of y'all may not have tuned in. I also know some of y'all may not have started studying until just now. Just as a quick recap, like this is like the recap of the recap, basically, because I recapped yesterday. So basically, you got your control systems, the basics of control systems. You got your closed loop, open loops for the opposite of this stuff right here. The grass, the output is like this, the air is like that. You might have a case where you have like there are cases where you have like oscillations. So, and an oscillation is basic. Man, I sound smart as heck, bro. I sound smart. An oscillation is basically when the graph goes like this and then comes back down and then it'll balance itself out. Uh, is this gonna update? Is OneNote gonna work today? I don't know if OneNote's gonna work today. Hold on, let me let me hold on a second, y'all. Let me close OneNote real quick. Um, let me close OneNote. See if OneNote. There we go. Now OneNote's working. Where's the Zoom thing? Okay, at first OneNote wasn't working for a second, but we just had to restart. We just had to refresh it. Okay, so yeah. So this sometimes you'll have a graph, it'll oscillate, it'll look like that right there. Um Basically your response will just look like the oscillation in terms of itself. You'll also have a derivative and that looks different. Refer back to the other stream. If you don't get it, refer back to the other stream. This is just a quick review. Then we went over Laplace transforms. Excuse me. Uh, you got your impulse function, your step function, ramp function, natural times the ramp function, the sine function, cosine function, natural times the sine function, natural times the cosine function, and you have their corresponding Laplace transforms here on the right side. There's a few properties of Laplace transforms that you can use here, and we did an example. We found example one, we found a time delay, did the Laplace transform of that, and this is what ended up what we have. It ended up being what we got when that was done. We got into inverse Laplace transform. This is for a repeated root, repeated real root. This is the incorrect way to do it. This is the correct way to do it. Uh, you end up getting this, like I was saying here, this, as long as the denominators are the same here and here, you can basically just have the tops equal the top. And that's what we do here. We have that breakdown. We have these equations come down to here. We get our numbers that we want. We have 2/3, -2/3, and -1. I think that's what the numbers were, right? Where's my where hold up. Yeah, here we go. So we have our numbers here. That's how that rolls. Complex roots. In the event of a complex root, you got to use the quadratic formula. You got that right there. We did the breakdown of this. I misspelled the word determine. Uh, Look, y'all, I was tired. Nobody told me I misspelled determine, okay? Nobody told me. Nobody told me that until I looked back and I was like trying to figure out what I was writing. And you're trying to determine A and omega. So let me determine oh, determine A and omega. Um Got the real part is A, imaginary part is omega. You got this right here. You got to leave the I and the J off, I or the J off. Step four, you plug in those values. You just start doing stuff like that. Um, Basically, you are able to combine these because these have the same denominator. These have the same denominator, so you're able to combine them. When combined together, these break apart. You just do the math, and that came out to something really not pretty. Came out to this. It's not pretty, but it's right. Final value theorem, Y of t, all that stuff. And then I said in the last one we were going to get to the we were going to get to the control design for a first order system, second order control systems, pole analyses, control design for higher order systems using root locus, and discrete control systems with the difference equation. So that's basically what we have today. That's what's on the agenda. Yeah, so that's currently what's on our agenda today. Um I do have food coming. Get your big back jokes out now at like 6 o'clock. 6:20. So we're gonna try and get through as much as we can in an hour. If we don't finish, I'm gonna just go grab my food and come back. Like it'll be like 5 minutes. All right. Relax. I'm not going nowhere. Uh uh hold on a second. All right. So with that being said, let's get back into control systems. First order systems with the time constant. Let's do the design for let's do the design. All right, yeah. Let's get back into it. Make sure that I'm recording the right side. Welcome to the stream. Thanks for being here. Yo, what's up, Journey? I was just thinking about you yesterday. I was about to say like what's up, see how you was doing. Appreciate you tuning in. Thanks for showing up. Um, but okay, yeah, yeah. I think this is the right thing. Yeah, it's on the right side. So let's go back into the final value theorem. Um So basically, the summary of the final value theorem breaks down to this basic stuff right here. It's basic but not basic at the same time. I'm just making sure that I'm not going to get fired. Yeah, I'm good. I'm not getting fired, y'all. um, so the final value. So let me just write this down. Chat, pick a color. Okay, sounds like gray. Sounds like gray is the option. If I had like 1,000 subscribers or something, or if I had like 1,000 viewers in the chat, I would definitely let y'all pick. But we ain't got time for we ain't got time to be waiting 15 minutes for people to pick a color. So the time constant theorem and the final value theorem. So okay, so the time constant theorem breaks down to this. For a given time constant equal to tau, tau equals um or the time a time constant tau equals, we'll call it a value, so like b2 over b3. And the time constant theorem states you have t of f, this is the final time value, equals b1 over b2s plus b3. That's as simple as I can break it down, but it only applies to a first order system. So like I need to write that in like some color that y'all remember. Write this in pink. Only applies to a first order system. You know what's crazy? If I became a TA for any of these classes, I could have gotten paid to do these things. It's all right though. I do this because it helps me study, and I hope it helps y'all study. So, um, a quick example drawing of this could be something like this. You got a a U going into a P with an output Y. You got a loop back, and then you have P equals B1 over B2S plus B3, and then tau once again equals B2 over B3. All right, cool. Everybody got that? Hopefully, I'm not saying it again, except for like 5 seconds from now when I say it again. The closed loop time constant. Golly, man, the closed loop time constant. So you have y over y of s over r of s, and that equals your controller times your power over 1 plus your controller times your power. And that's basically what we've been doing this whole time with that block diagram. You got your C here, you got your P here, and you got your Y here. And then this all feeds back. And let's say this is like U or something like that. Like it doesn't really matter, but to avoid confusion, this is essentially what you got right here. Um, the final value theorem, however, let's pick a fun color, like a nice bright orange. Yeah, yeah, y'all. I'm about to get disowned by the Texas A&M family. Look, y'all, this is Bengals orange, not that ugly disgrace of a color that I also don't entirely disdain. Look, look, I'm an Aggie that likes orange. Is that so wrong? I'm gonna get arrested next time I go out on campus. Oh man. Okay, but anyway, that being beside the point. Uh yeah, that being beside the point, the final value theorem applies to any order system. Now, it's important to it is important to note, if it's not on here, if any part of the system fails the final value theorem, so if any so like if any part of the system does not terminate, the final value theorem fails. The final value theorem is used for signals. And final value theorem can only be used if there is a final value. All right, so final value theorem, I think that's everything. Everything that has to do with final value theorem. Any questions? Any questions in the chat? Anybody got questions? Nope, no questions. Look, got questions, ask them now. Ask your questions now. Ask now. All right. I don't see any questions, so we gonna move on somewhere. Um. Oh, hot cheese. This is a lot more than I thought there was. Okay, so let's do an example of the final value theorem when might it might not work. It might work, it might not work. So let's do an example. Y'all can see y'all can see everything, right? Yeah, y'all can see. Y'all can see. Y'all can see. Y'all good. All right, let's do an example, y'all. Let's do a nice, fun example. We'll rewrite that because it looks bad. Let's say we have a U here going into a signal of 5 over S minus 5. That's a bad idea. We'll do 6 over S minus 6. That way we don't confuse 5 for S and S for 5. Then that comes to an output of Y. Well, if we're going to do the final value, and we'll say that the U of S is 2 over S. That's what we'll say. So we know to get the final value theorem of this, we need to do 6 over s minus 6 multiplied by 2 over s, and then that's this equals y of s, and then we need to multiply that by s. Well, y of s times r of s times s. R of s is that 2 over s. That's what that is. That's this right here. Um, so for final value theorem, we need to take the limit and then do 6 over s minus 6 times 2 over s. Then multiply that by s. Well, we know that s's cancel. You end up getting 12 over s minus 6. At s equals 0, you get -2. But we got to validate that. We need to validate this in time domain because this may work, but it might not. Doesn't seem right. So validate in time domain. The way we do that is we go back to our basic Laplace stuff. Uh, uh, think up, think. I lost my train of thought. We got 6 over s minus 6, 6 over s minus 6, and then that's multiplied by 2 over s, and that equals our y of s. Now we go back to our basic Laplace stuff. All right, basic Laplace, basic Laplace. I'm sorry, y'all. I'm just trying to make this interesting for y'all. I need to focus and just do the look. I just need to focus, do the dang problem, do the dang thing, right? So we got C1 over S minus 2, not S minus 6, and that's plus C. Oh, gosh, dang it. C2 over S. Um, so I think I did this with the mirror method. I think so. This is so C1 over S minus 6 plus C2 times S minus 2. Oh, that's right. This is the cover up method. The cover look, hey, I'm reminding y'all of the cover up method. I almost forgot how to do it myself. So we got to multiply by S minus 6 on all the way around. So we got C2 times S minus 6 in parentheses over S. So this is like So just make that little note, S minus 6, multiplied on both sides. And then that's supposed to equal 6 over S minus 6 times 1 over or 2 over S. Um, and this is times S minus 6. Got to be careful with those parentheses. S minus 6. So this S minus 6 over here, that cancels with that. That jump cancels right there. Um, and we'll solve this at S equals uh S equals 6. So we get at the top C2 equals 0 over 6. Uh and we have 2 over 6 here. So we end up having C1 uh yeah, C1 equals uh 6 times 1/3. C1 equals 2. And then we do the same thing on the other side. Uh do the same thing to the other part of the equation. Yeah. Sorry, I'm like lost my train of thought and I thought I messed up. I didn't mess up. I'm good. So we got C1 S over S minus 6 plus C2 equals 2 over S minus 2 times 1 over S times S. Um say S equals 0. That cancels. You got C2 equals 2 over negative 2. That's times 2. 2 over negative 2 times 2. So that gives us negative 2 equals C2. Um, so that breaks down into us having e to the 6t minus 2. Well, that graph, oh, y'all can't see it. Hold up. Sorry. That gives us that graph looks like this right here. That doesn't terminate. That means final value theorem failed. FVT failed. So the final value theorem doesn't work with that. Um, all right, so moving on. So I think everybody got the final value theorem. Any questions? Questions in the chat. Anybody got questions? And ask your questions now. Anybody got questions right here? Give y'all a second. No questions. All right. No questions. Let's move on. Let's keep it. Let's keep, as Dash would say, let's keep it going. Keep it going. Um, Also, by the way, y'all, I straight up am just like I'm basically rewriting the notes. So like if y'all don't understand what I'm saying, go back and talk to the professor. Go talk to the professor. I mean, you can't now because exams tomorrow, but I mean you could email him. You can email him. You can send an email. You know, you could send an email. Um, I'm just like trying to read through this like quickly to see like what a brother can do. How do I have this sorted? Oh, my bad. I was it's going backwards. Backwards in time. Um Repeated routes, study sessions, second order system, second order systems. I got there. I look, let me just make sure that this is the correct information. Yes. Yes. All right, second order system. Yeah, we're back. We're back with it. Back at it like I'm back at it. You know what I'm saying? Okay, my food got ordered, or my confirmation of food order just came to my phone, or came to my watch. I mean, I gotta pull my nose. Y'all, this weather changing too much. This weather play too much. Hold of a transfer function. All right, so uh let's go back to the left side of the screen. So as you can see, this is all we did. Look at all this work we've done so far. Look at that. That's a they should put that on the front of cars, man. Y'all can't tell I love my boy Kareem Biggums. Kareem Biggums, successful moves. Okay, there we go. I had to like draw a mark so I could know where to start writing. Okay, so poles of so like second order systems, the first thing we're going to work on is you got to find the poles of a transfer function in the S domain. All right. So let's say poles. What zoom is this? 50? I need it to be 100. So the poles of a transfer function in the S domain. So in the S domain, it's a little bit strange, but I'll break it down for you now. You know, the imaginary plane. That's where I get all my fun. That's where all the fun happens. Like Anakin Skywalker song. Like Anakin Skywalker says, this is where the fun begins. All right. So you got your imaginary plane here because the color orange doesn't exist in Aggieland. I don't understand it because I'm from Virginia where got maroon and orange just bleeding through everything. Got Virginia Tech Hokies and Mountain View High School, and I'm just saying it doesn't make any sense why orange and maroon can't exist can coexist in peace. I'm just saying I'm just, like no shade. Oh man. So this is the real and imaginary axes. So like we know that in the real domain in the real domain that e to the minus 4t comes out to the s domain as 1 over s plus 4. Wow. Well, would you look at that? That's crazy. That's wild, bruv. Absolutely bananas, cuz. Well, we'll say that this right here is 4. If you remember back from algebra, I think it's algebra. Is it algebra 1? My viewers that are just now entering high school, is this algebra 1 where like you learn that when it's plus it's in the negative side and minus is in the positive side? It's been too many years. But we'll say that this is -4. We're -4. That pole is going to be right there along that line right there. That's where the that's where this value is. Um, if I had like, for instance, we gonna do this in I should have done that in blue, but it doesn't really matter. If we had like this one right here, if we had a g of s function that was like 1 over s squared plus 4, well, we know that s1 equals 2j, and then s2 equals minus 2j. That's the kind of stuff that just happens. It is what it is. Um, um, so that's gonna end up being here and here. So we'll say that this is 2, this is minus 2. These are where those points will lay on the imaginary plane. So basically, you got to work with both and both. You got to work with both of them in the imaginary and the real plane. Um. So uh. So a easy way to look at this is that signals. So how do I put this, man? Hmm. Let's do a couple more examples so I can illustrate this to you people um eloquently. Y'all like that English 210 word? Eloquent. I think I can spell it. Don't This is not a spelling class today, so don't ask me to spell nothing today. So we have let's say we have g of s equals c1 over s minus 4. Well, we know that s is going to equal 4 in this case. That's going to be over here on this part of the plane. We'll say this is 4. That's where this is going to equal. That's where it's going to equal 0 in the s domain. Um, So yeah, and what ends up happening is we have our G of T is equal to 4 times, well, it's not four, C1 times 4 or E, gosh dang man, like times E to the minus 4T. Well, that graph, uh hold on, look, I need Desmos for this. I need Desmos. Cause like I know what's happening, bro. Chat disconnected. What the freaking. So like I know kind of what some of these graphs look like, but like I can't always I can't always remember stuff. So let's say we have like E raised to the minus X. So with this, the way the graph is going to look is it's going to come down here and it's going to be going like this, but it's never really actually going to touch zero. That's that graph. Uh, yeah, I just need to verify it real quick. Verify what the graphs look like. If you get a sine function multiplied by it, so if I did like sine of x, say sine of like 5x. Oh, cheese and crackers. So if you get a sine function, um, if you end up having a sine function, it's gonna be, let's do this in pink. So like we have a uh e to the minus 2t times sine of 2t is gonna look something like this, but it's gonna oscillate forever basically. Um and I was doing all these examples. I know it sounds like a waste, it seems like a waste of time, but trust me, I was doing this to prove a point. So as you can see here, the orange, if you look here at this orange part right here. You look here at the orange. You see how the orange is nice and stable and it's just sitting there. You see how this blue dots, they're just like, they're a little weird, but they're just sitting there. But everything else is just gone, just out the gate, just gone out of there. Like crazy stuff. That's because anything signals on the right half plane are unstable. They're like the Joker. Signals on the right half plane. So this is the right half plane. So signals on the right half plane are unstable. If a pole is in the left half plane, that's where you want to be. That's those good old A whoop people right there. That's the stable people. The people that have the head on straight. The ones that went and played basketball at the gym and they go home and they tell their mom like, "Hey mom, I had a great day today." And they go to class and they study hard in class. That's the left half plane people, man. The people with the head screwed on straight, that's the stable people on the left half plane. The right half plane is like every Batman villain that has ever existed. Easy to remember. So let's write that down right here. If a pole is on the left half plane, it will be stable. And then anything that's on the imaginary axis, things on the imaginary axis, let me make sure I write this correctly. If it's on the imaginary plane, it will be marginally stable. Okay, so that's like the rules of like how planes dictate whether or not a system is stable. Um, so there's a great picture that I'm just gonna show briefly. There's a great picture I'm gonna show briefly. All right. See that? See that? Look, left half plane, all these are stable. This is all stable. All this stuff terminates. Right half plane, those are not stable. Those don't terminate. All right, bet. That's it. That's it. That's it. That's it. If you missed it, go pause the video. If you didn't get it, if you don't even know what's there, that's not my fault. You can also kind of like find this like later on. Um, but essentially what that means, everything that I just explained there, um, what I basically just explained there for controls for the control design, for control design, all poles need to be in the left half plane if even if one is in the right half plane, the system will be unstable. All right. All right. Everybody got that? Any questions? Any questions in the chat? Questions? Nobody else in the chat. It's just me. Nah, it's cool. It's cool. It's y'all's grade. It's not my it's like it's my grade too, but it's y'all's grade. It's y'all's exam. Y'all want to spend your time studying or playing fork knife and cuphead and cup skull and all that. Y'all want to hey, it's y'all's grade. I'm just saying. So let's just say we have a higher order control system. All right. Let's just say we have a higher order system. So let's do this right here. Let's do it. Let's do it up real nice. Let's say we got a higher order system, right? We have a got some type of input goes into here. We got our controller. That goes into a box. Some function on the top. You got A2 times S squared plus A1S plus A naught. And then that comes out to a Y. This is our plant. And that loops back to the input. So higher order control system. Um, I'm not going to do the simple example. I'm going to jump right into the electrical example because you know me. If you know me, there's three things that I love: football, video games, and electricity. You mean to tell me you didn't know I love electricity? You've been watching these videos for how long? All those study sessions and electronic systems, and y'all don't know I like electricity? Nah, it's fine. Nah, it's cool. It's cool. I'm about to trip y'all up right here. Y'all really sleeping on your boy. Y'all really sleeping on me, thinking like I don't know how to do this stuff. Watch this. Watch this. Put some music on real quick. Hold on. Let me. No, I'm kidding. I'm kidding. I'm kidding. But no, like y'all really sleeping on me. Look at this. Bam. U of T. You got a resistor. Boom. Inductor. Boom. Capacitor. Boom. Boom. Dot. That comes out to a load. And we want to know what the load is. We want to know what the load is here. What is YFT? What's the output? What's the output? Huh? I bet you don't know what the output is. What's the output? What's Y of S over R of S or over U of S? What's the answer? What's the answer? Go ahead, go ahead. No, because y'all want to sleep on me. Y'all want to sleep on me about me not knowing what the heck's going on here. This is a resistor. This is an inductor. This is a capacitor. Tell me what the answer is. You can't. Well, you probably could. If you've been in the class, you probably could. Let's just go through the solution together, shall we? So the solution, you got U of T. You got your voltage across the resistor plus the voltage across the inductor plus the voltage across the capacitor. Okay, how much time do I have before my food gets here? Let me see if I can answer this before my food's supposed to get here. Because if my food get here, I gotta go get it, man. I can't be okay. I got about 5 minutes. I got about 5 minutes. Okay. 5 minutes. Speed run. So the voltage across the resistor is just gonna end up being the voltage. So you're gonna have R times IT. Voltage equals V equals IR. So V equals IR. Is that y'all? Yeah, y'all can see it. So R equals R times IT. That's plus the inductance multiplied by the derivative of the current times T over dt, and that's plus Y over T because the voltage across the capacitor is the same thing as the voltage that we're trying to figure out. Trying to figure out that voltage right there. Um, we know we know from this part of the equation that that I of t is equal to c times dy t dt. So breaking this down even further, this second breakdown, you really have r times c times dy. By the way, we're trying to get everything in terms of yt dt plus lc times d2 yt over dt. That gives us uh if we get that in the S domain, so bring it back to the S domain, back to reality. Well, I guess imaginary land. You get of R times CS of Y over of YS plus LC S squared YS plus Y of S. Now that's all equal to U of S. This equals U of S. So in order to get this broken apart, we just got 1 over RCS plus LC S squared plus 1. And that equals Y of S over U of S. Now, this looks real confusing, right? This is like, how the freak did he figure this junk out? What is this dude doing, man? How do you do that? I got you. Then I gotta go get my food. All it is, you just gotta summarize this into a generic phone. This is just it's just an it's just the application of the generic form to this problem. You got you got gamma times zeta n over s squared plus 2 times zeta n omega n times s plus omega n squared. All right, hold up, y'all. I'm a be back. Give me like 5 minutes, y'all. Uh, give me a few minutes, y'all. I'm gonna be back. Take food break. I'll be back. Give me a second, y'all. Be patient. Be patient. Patience is a virtue. Patience is a virtue of the ninja. Remember that. Okay, y'all, good guys, I'm back. I'm back. All right. I'm back. I'm back. All right. Relax. Don't worry. I'll go back and edit it and cut the time I was out from the stream. Okay. It's also like 60 degrees outside. And I'm talking like a cool 60. Anyway, I'm back. Uh so I gave y'all the general form of the equation. The general form of the equation. So you have a you have zeta. You have zeta. Zeta Zeta is the dampening ratio of a second order system. So you got zeta. Zeta is the dampening ratio. You got omega, which is the undamped natural frequency. If I could spell frequency, if I could spell frick right, frequency. So that's undamped natural frequency. And then you have like some type of gamma ratio. Now, gamma ratio, I believe in this class is just typically one, but this is a ratio. Um, it's important to note that you want to have at the beginning of the S squared, you want to have 1 times S squared plus 2 zeta n omega n S plus omega n squared. Um, so just to plug everything in and give y'all kind of like how this breaks down. Um, we know that in this event that omega squared with the frequency, the not frequency, the RLC circuit, the RLC circuit thing um equals 1 over LC. That's omega squared. That's omega squared. So omega equals 1 over square root of LC. Omega, that's what that equals untouched. Because if you look oh, because if you look here, where is it? Where is it? Where is it? Did I write that wrong? I might have written that wrong. No, I didn't write it. I didn't write it wrong. I just wasn't really expanded upon. Um. Oh, that's what happened. So what I did to get 1 over LC is I just made one equal one equal 1 over LC. And you just do that by dividing, I believe, by LC. Yeah, you do that by dividing LC. So that's how that breaks apart into that. Um, then since we know what omega n is, we have two zeta n times omega n equals R over L, which really is R over 2 omega L, which is really R over the square root of C over 2 square roots of L. That's just how it ends up breaking down. I'm not going to go through all the algebra. Just trust me on this. And then you have your zeta value, zeta n equals to R square root of C over 2 square roots of L. Um, then we have different cases. You have different case values. It's like case one. Zeta is greater than 1. That means there's two distinct real poles. That means that S1 equals minus zeta. Oh, geez, that was a horribly drawn zeta. Minus zeta n, omega n plus omega n times square root of zeta n squared minus 1. S2. And this comes from the quadratic formula. If you did the quadratic equation with these values, if you did the quadratic equation with these values, you'd find the same thing that I'm writing down here. I just didn't feel like doing the quadratic equation for it because it takes a while. So zeta omega n minus omega n times the square root of zeta n squared minus 1. Thus, the two distinct real poles um, and two distinct real poles makes this an overdamped system. So yeah. Sorry if you've been here for a while and like I high key was just AFK. Um I was just trying to get my food, bro. So overdamped reduces vibration. It's kind of like this. Let me show y'all like an example of like can y'all see the ground? Here's an example of what it's like when you have like an overdamped system, right? All right, look. If y'all can see, y'all can kind of see. So like, if I were to over dampen my body, right? I'm doing push-ups. I over damp my body. There's no bounce. As you can see, there was no bounce with that. That's over damped. I'm putting a lot more effort into that push-up to prevent myself from from vibrating when I go back up. Because I could have bounced off the ground, and then that's like just basically letting gravity and force and everything bounce back, but making sure I over damp my body and pushing all the way back up, you're reducing the vibration with an over damp system. Um, so yeah. Uh you have case two. You have case two. Identical real roots. or repeated real roots. That's when zeta n equals 1. So that's when it's critically damped. That's when it's just perfectly good enough to break us to that's when it's just perfect. Excellent. Just it's right there. It's just right where you need it to be. You'll end up having let me give y'all the equations that you'll use as well, because y'all might need those. So this is where you'd have like this is the case in overdamped where you'd have like C1 over S plus A1 plus C2 over S plus A2 plus a C3 over S, however many times it needs to go. With the repeated real roots, um, this is a critically damped system. I don't think I wrote that down, but this is critically damped. So this is critical damp. Not to be confused with moist critical, the commentator, because moist is another word for damp and critical. I'll just. Okay, so some dude just walked out looking extra sad or something like that. I think that was the old Chris the Ninja. I'm the new Chris the Ninja. All right. He looked out looking real sad, man. Like someone didn't laugh at a terrible joke or something like that. I don't know. But this is a critical. He told me that this is a critical damp system, and burst into tears and ran off like down the hallway, I think. Um, but yeah, basically that graph is going to look like this. You're coming up here, and it's just going to line up right there. It's gonna hit that line. It's going to stay critically damp. And your equations for that are C1 over S plus A1 plus C2 over S plus A1 squared plus C3 over S dot dot dot, as many as you have. Now, you could have your third case is underdamped system. That's when you have 0 is less than zeta n, and zeta n is less than 1. So you can't have zeta n be less than 0. But if it's between 0 and 1, it's underdamped. Um, this has the fastest response time, but it has quite a bit of quite a bit of wiggle with it. So this is where you'll start getting into like an S1 value where you have zeta n omega n plus j omega n times the square root of 1 minus zeta n squared. Then you have S2, which is the same thing, except you have a minus sign. So you have zeta n omega n minus j omega n square root of 1 minus omega n squared. Got it? All right. So then that's when you have your cool looking equations. You got your C1 times omega over S plus A squared plus omega squared plus C2 S plus A1 over S plus A1 squared plus omega squared plus C3 over S. That's where you get that one from. Get those cool equations right there. Look at that. And you'll end up having a graph that will be represented by something like this. So it's gonna go up, and then it's gonna come down, and then it's gonna balance out. And then this C3, that's the C3 value right here. That's where C3 is. So let's do a quick example. Yeah, example time. Everybody got that. Everybody good? Y'all good? Y'all need a snack? Okay, cool. Everybody seems like everybody's good to go. Let's get it cracking. All right. Let's get it cracking. I ain't talking sea monsters. I can see now why the old Crystal Ninja just left. Just straight up left. Okay, so you get y over s, y of s over u of s. That equals 1 over s squared plus 4s plus 10. And that equals some box value over s squared plus 2 zeta n omega n s plus omega n squared. All right. Okay. So we know from oh, y'all can't see it. Why don't nobody tell me this stuff? Somebody tell me and you can't see it. This is why I need people in the chat. This is why I need people that everybody like, oh, I don't want to study on the stream with you. This is why I need people in the stream with me, man. So I can like when you can't see it, I need you to tell me I can't see it, y'all. Jeez. Now I gotta give y'all a second to write up and catch up. Y'all got it? Okay, cool. So and uh geez. Okay, so we know that omega squared, this is omega n squared. So we know omega n squared is that value. So we can say omega n squared equals 10. So if we square root both sides, omega n equals the square root of 10 plus or minus technically. So now, when we break it down even further into, when we come back over here and break it down even further, we got 2 times zeta n times square root of 10 equals 4, right? Well, we need to divide out 2 times square root of 10. So zeta n equals 4 over the square root, 4 over 2 times the square root of 10, which actually ends up being 2 over square root of 10, because you can divide the 4 by that 2. You could break this down further. I can't remember all the algebra square root rules and stuff like that. I really can't remember right now. So we're just gonna leave it like that. We're gonna leave it like that. So we know zeta n is 2 over the square root of 10. Now let's say we have a block diagram that looks like this. We got an R value. Let's say we got an R going into the control. We have a KP that's coming out of there. And then we got got 1 over s squared plus 4s plus 10. That goes out to a y, and that loops back to here. That loops back to here. So we know what we're getting ourselves into, right? We know we have we need to get our transfer function, and that's our y of s over r of s, or y of s over u of s. And that's going to be kp that's going to be we'll call this u and g. So u and g. We know we're going to have u times g over 1 plus u times g. All right. Well, that breaks down to be kp times 1 over s squared plus 4s plus 10 over 1 plus KP times 1 over S squared plus 4S plus 10. Now we can break this down even further, and with some magic algebra, some magic math, we can get this to look like, we can make this look like Ice Spice in terms of math numbers. Look good, man. We got KP over S squared plus 4S plus 10 plus KP. Look at that beauty right there. Look at how nice that looks. Looks a lot better than that ugly equation over there. That's the equation that looked like me for real. Nah, I'm just playing. I'm not that ugly. Y'all can laugh. That is a joke. I am okay. Like y'all can laugh at that. I'm not gonna be mad. So step two is to identify the dampening ratio. So step two, well, we know it's a closed loop, and we can say that omega n equals the square root 10 plus kp. Now, how do we know that it's a square root of 10 plus kp? Well, it was a square root of 10 before. We're just adding kp to it. So kp plus 10, or 10 plus kp is now omega n squared. So you square root both sides, you get kp plus 10 or 10 plus kp. However you want to write it, it's a plus sign. Doesn't really matter. We get that. So now we go back down and we break it. We put that into we go back over here and we put that into our 2 plus our two times zeta n, so 2 zeta n omega n equals 4. Well, we need to figure this junk out now. You know what I'm saying? Like we can't be crazy people out here. But we know that from the last part of the problem, zeta n equals 2 over the square root of 10. But we now just need to add kp because that's what omega n is. Um, so for an overdamped system, the ratio has to be a real number. So you have square root of 10 plus kp has to be greater than 2, greater than 2. Because if it's not greater than 2, you're gonna end up having having some very, very not real numbers. And we know it has to be greater than 1. Um, so in order for this equation to equal 1, it has to be greater than 2. So this has to be less than 2, so it can be greater. Y'all get. I think y'all get what I'm trying to say. Y'all get what I'm saying, right? No. Well, let's continue then. Square both sides. You get 10 plus kp is less than 4, and then you say that kp has to be between -10 and -6. So kp has to be in between -10 and -6. So this is where we get to so all this is basically like just how to find the dampening ratio, the damping ratio. Any questions about that? Any questions about damping ratio? We got what? Got one viewer. Oh yeah, we got one viewer, one consistent viewer. Think that's myself. Self five. Let me go wash my hands real quick. Because I'm about to I'm gonna wash my hands real quick. Okay, so we back, hands washed. Just negated that with my blowing my nose. But we're gonna get this, we're gonna get the paper towels. We're gonna eat some food real quick because your boy hungry. I need to eat something, man. My pen is right here. Okay, so now we're getting into the analysis. Getting into the analysis of a second order system. So we have, it doesn't really matter what we have on the top because it ends up being the same no matter what. So you have your random whatever value on top of the equation. You have an s squared plus zeta n omega n s. I think I'm missing a 2 plus omega squared. Um, so let also you can test all these with the step response. The step response is just a general easy test to do and the easiest one to work with. But usually, if it passed the test for the step response, it will pass all of them. So let's say we have a graph, we have some output here. So you might have an overdamp system, which comes up to like right there. You might have a critically damped system, which is going to come up. Oh, that's too close to the same color. Let's do so you have a critically damped, it's going to come a little bit faster, and then you have an underdamped system. It's going to shoot up here and then mellow out to where you need it to be. So this is the 0 less than zeta n less than 1. This is the zeta n equals 1. And then this is the zeta n Greater than one. So give me a second to take a bite to eat real quick. I'm only gonna take a couple bites. This ain't a mukbang. This study session. But sometimes you gonna eat while you study. I'm not sponsored by them, but if you need a good burger, Burger Mojo. Shout out to Burger Mojo. One more for the road. Mm. So let's take a look at an underdamped second order system. So you're gonna have a few parameters that you're trying to find. You want to find your setting time. So setting time, TS. You want to have your peak magnitude, which is the magnitude of overshoot. You have your peak time, which is the time to reach the peak, which kind of self-explanatory. Like I said before, TS is setting time. The T is usually capitalized. And that's usually a percentage. That's usually a percentage that you want to calculate. So it might be 1%, 2%, N%. You'll also have a TR value. That's your rise time. And that's time from 10% to 90% of final value. So the next part that I was going to cover isn't going to be required on the exam. I think it's just like solving something for this. Oh, yeah, Burger Mojo. Not sponsored, but shoot, I wish. My big self, I wish. Mm. So instead of showing how to solve for everything, I'm just going to give you all the I'm going to give you all the equations that you will likely use on the exam. So how to find overshoot. If we know peak time. Well, MP equal is this equation right here. E to the minus pi times zeta n over square root of 1 minus zeta. Gosh dang, why do I always write this like this? Negative pi times zeta n over the square root of 1 minus zeta n squared. That's how you can find the percent over the overshoot. If you want the percentage of overshoot, we'll do this in orange because I just want to make sure that y'all see it's different. You do 100 times e to the minus pi zeta n over square root of 1 minus zeta n squared. That's it. For setting time, do that in blue. Usually you're going to be given a percent. You want a percent of setting time. That's going to be it's going to be e to the minus zeta n omega n times t equals 1%. 1% also equals the 1% setting time equals minus natural log, oops, natural log of the percentage, so 1% over zeta n omega n, which in this case is minus 4.6. Oh, wait, hold on. No, it's just 4.6. Oopsies. 4.6 over zeta n omega n. Because when you take a percent, when you do a natural log of a percentage or a fractional number, you don't get you get a negative number. Because if you remember from like exponents and logs and stuff like that, when you raise to a negative power, It gives you a decimal. When you raise to a positive power, it gives you, you know. So you might be asking, hey, Chris, hey, bro, how do I do the other percentages, man? Look, man, look, bro, I got you. Any other percent, I believe it's n percentage, any percent, no speed runs. Take the natural log of the n percent and divide that by omega n, or not, yes, omega n, but zeta n times omega n. Um, and then the percentage of setting time. So this is the note in case professor asked this. Percent setting time is total time for the system to settle within the percent that you want of the values of the time values. Hope y'all can see that. So this is the so I'm just gonna like copy this. Um, this is so this is the summary. Y'all take a second and read that. Any questions in the chat? Any questions? Questions? Questions are being taken now. Any questions? I'm gonna take a bite of my food real quick so y'all can read that and write that down if you need to, or correct me if I'm wrong. Good freaking burger, man. So it's important to note that changing the pole location can change the response for your control design. Um, I'll copy this over here as well. This might be important. By the way, these are all the notes that I've written down. So like I'm not stealing these from anybody else. These are the notes I wrote down. This is my copyright. My copyright, all right? Okay, so we're actually almost done. Um the only thing that I haven't covered so far is root locus and digital control systems. So we're gonna cover the root locus and stuff real quick. Um, yeah. So let's just go ahead and scroll down real quick. Make our little split line. And we'll start off with root locus real quick. Root locus doesn't take that long. So this control design for high order systems. So in general, if we had if we had an R we had a control system, a control block diagram. We got RS coming in here. We got KP and a G of S. And then that goes to an output Y. Doesn't really matter. And we say G of S is equal to some BM S to an M plus BM minus 1 times S to the M minus 1, blah, 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 plus B naught. And that's over A to the N S to the N plus A to the N minus 1 S to the N minus 1. And the reason I'm like emphasizing these so much is because I want to make sure that y'all write this down correctly and that I'm explaining it correctly. Plus dot 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 plus A naught, where N is greater than M. Okay? N is greater than M. So you got your closed loop transfer function. Let's say you got a Y of S over R of S. Like I said, it doesn't really matter. It's just KP times G of S over 1 plus Kp G of S So we're going to solve for the poles of the first equation. We'll call this equation 1. So the poles can be represented as a function of Kp. So the root locus is just a graph it's the graph of all possible poles of equation 1 relative to the parameters of Kp. Hold up a second, y'all. All right, so a root locus is the graph of all potential possible poles. That's what I was trying to clean up. Poles of of equation 1 relative to the parameter Kp. So that's when Kp changes from 0 to infinity. Jeez, there we go, man. Oh yeah, bruh. Had that neck crack in it. Man, when I tell you, my neck be stiff. It be rough out here for your boy. So let's do an example. Let's do an example, all right? Because we just had a bunch of like hogwash and gobbledygook, as Charlie would say. Um, but let's get it down here to this. So you get y over y of s r of s equals Kp times 1 over s minus 1. Oh, let me draw y'all an example. I'm just getting lazy on y'all now. Let me not be lazy on you real quick. You got R of S that goes into this. You got so you got a Kp and you got a 1 over S minus 2. 1 over S minus 2, all right? Some simple. Got a Y out here. This comes back and that loops back to there. Bam. Boom, bam, bop, bada bop, boom, pow. Insert your super hot fire meme now. Okay, so you got y over s, r of s, and you have kp times 1 over s minus 2 over 1 plus kp times 1 over s minus 2. Now that's going to be kp over s plus kp minus 2. That's just how the algebra lines up. Don't ask me. I mean, you can ask me. I sometimes I get it, sometimes I don't, but I just happen to understand this one here. So so we want to have S1 equals minus KP minus 1. So when KP is 0, so we'll say let's draw our graph right over here. So we'll say at KP equals 0, S1 will equal S1 will equal 2. So we put that like right there for 2. When KP KP equals 3, S1 equals minus 1. And then when KP equals infinity, S1 equals minus infinity. So we know that the whole time that we have KP and S1 is going to be going this way. And it's going it's infinitely decreasing. Trying to figure out what other example would be the most helpful to do here. So give me just a second. I'm actually going to take a bite to eat while I figure this out. This good burger, man. Hey, food companies out there. If your food good, sponsor your boy. I mean, doesn't have to be money. 10% coupons. Big burger. Okay, so it looked like all right, I'm gonna do this. I'm gonna do this this problem right here, but I'm gonna modify it a little bit. Modify it. There's the only one I'm gonna do. So once again, let's say we got a well actually, let's do the little harder one first. Let's just do the harder one. The one that's a little bit more difficult, or a little bit more complex, I should say. So let's say we got a say we got a thing, got a circle plus minus KD S that goes into this, and we got a KP here that goes into that. That goes out to a 1 over S squared plus 4. That's really zoomed in. I did not realize how zoomed in that was. So we know that we got for this one KDS plus KP. So we know that the equation is going to end up being KDS plus KP over S squared plus KDS plus 4 plus KP. That's just what we know. That's what we know so far. So we make KD equal to point 0.4. We make KD equal to 0.4. 0.4 times KP. Then we can have our equation end up being 0.4 KP S plus KP over S squared plus 0.4 KPS plus KP plus 4. Now we can get the root locus of the equation. So we know that B, our B value, is minus 0.4 plus or minus the square root of 0.4 squared minus 4 times 4 plus KP all over 2. Well, value is this. Um, sorry, y'all. Group chat popping off. Uh, so we have the root locus of equation 1. So we got minus 0.4. So this is the root locus of equation 1. Let me lasso all that. But a bop boom. Pow. Erase that. Hit that. Bam. Okay, and now what we can do is we can take our S1 equals to 0.1 or 0.4 minus the square root of 0.16 minus 4 times KP plus 4 over 2. And then that equals 0.2 times 0.2 minus or plus or minus, I guess, square root of, I think it would be 2 1 minus KP plus 1 squared. I think that's what it is. I think so. Uh, Send invitation. Oops. Oh, 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 oh. Hold up. One of my friends is asking like for my invitation thing. If it doesn't work, my bad. Um, but yeah, so that's basically how you do that equation there. And then yeah, essentially you have your root locus, and at certain points, like when you're S1 at your S1 point, so it doesn't really matter too much, but like we'll say S1 and S2, that equals zero point 0.2 plus square root of, we'll just like keep it in the long form so that way like I know it's correct. Dang it. Hold on a second, y'all. Don't remember if I have a password on here or not. Uh, I don't think I have a password on here or not. I don't think I have a password. But anyway, but anywho, just to make sure that I stay consistent and have like the actual correct answer in case I made a math mistake, because you know me and math mistakes go together like mashed potatoes and gravy sometimes. So if I got zero point 0.4 minus square root of 16 or 0.16 minus 4 kp plus 4 over 2, and then that's 2. Let me lasso that, move that down. Bro, I swear these people be so loud, bro. Like you think I'm loud. You think I'm loud? Bro, it's not comparable. It's not comparable. So zero point 0.4 plus square root 16 minus 4 times kp plus 4 over 2. So like let's say that's let's say kp is 0. That's gonna be 4, 16, 4, 0, 4, 16, 16 minus 16, 0. So that's just gonna be like point 2. It's gonna be a plus point 0.2 and then a minus point 0.2. Let's say KP is negative 4. KP is negative 4. That's gonna end up being 0. It's gonna end up being square root of 4. So uh yeah, square root of 4 It's just our square root of 16, which is 4 over 2. That's just 2.4 plus 2. So 2.4 might be like right here, and then minus 2.4 right there. So we know that it's going to basically be going up like this. And as K, and if KP goes to infinity, then as KP goes to infinity, like it's that's as it goes down, it's gonna keep going like this. And as KP approaches infinity, so like let's say we have like a really let's say we have a six 12 16 times 4 64 um give you like negative 48 negative square root of 48, that would be zero point 0.4 negative. That's going to just keep climbing up this that's just going to keep climbing up that negative I value, but it's going to stay consistently at that. So we know the root locus is going to go up like that. Um, I don't think so. Let's see. So the last thing is basically the digital control systems. Dang. Hold up. One of my hold on a second, y'all. Uh okay, there we go. Had to pause it for a second. think it should only be sharing. We're good. We're good. Yeah, still only sharing the same thing. But one of my friends is having a question. Maybe I can answer it. Prove to y'all I'm not just like talking crazy. Telling you, if you've never been to Burger Mojo, get there. Not sponsored. Y'all want to see that? Got any questions? Riker, to answer your question, I'm doing control systems. This control systems for it's a fourth year class, level 4 class in my engineering department. It's not that bad. Like it looks terrible. It's not that bad, actually. Also, if we finish this, I'll probably play Cuphead tonight. Maybe. I don't know. Maybe. Let's see. We just gonna keep it going for now, so we can hopefully finish this. Knees, bro. A knee. So digital control systems. Sometimes sometimes you can't always have an analog system. Sometimes it just ain't gonna happen. Sometimes you just cooked. It is what it is. Um sometimes it just isn't in the stars for y'all. So let's say we have a let's say we have a R with an E. Oh frick, that is an ugly E. So we got an R with an E that goes into a controller, C that goes with the input to the physical system of the plant, and that has a Y, and that comes back around to this. So you might end up having a system like this, but oh no, oh no, man, the system the it's only sampling at certain points. So you got like a system going like this, and you can only sample here and here and here and here and here. So like that's digital. It's discrete values that it's pulling from. Now there's a couple scenarios that need to be that I don't think this is actually on the exam. I can't remember if he said this is on the exam or not. So he might actually be done and I'm just doing extra. Um, but the scenario is if you can have a couple different scenarios. So scenario one, scenario one, uh the sample interval is small or the sample rate is high. This can directly implement a sampled control signal. Like you can directly implement a sample control signal. Gosh, why don't y'all tell me this stuff, bro? Y'all some terrible chat, man. Y'all are terrible in the chat, bro. No, I'm kidding. That's my fault. I should know better. So an example of this would be like if we had a signal that goes like this, and we sample from here to here, well, from there to there, from here to here, nothing has really changed, and it's a pretty small sample of what's there. So we can implement a direct sample of that control signal. However, if the sample interval is large, then the sample control signal may not represent the original continuous signal well. So it may not represent the original signal well. Now, that's not saying it will never uh now it's not to say that it will never represent the signal well or that it can't represent the signal well. For example, if you had a control signal and this went on for like 5 hours and you sampled here and here, well, this would be well represented. You wouldn't know it's well represented, but you know it is. You know it's you wouldn't know it by the computer, but it doesn't change at all. So it's pretty easy to assume what it's going to look like from that point to that point, as opposed to if you had this graph and that lasted 5 hours, and you sampled here and here. Well, there's not enough. Oh, y'all can't see that. If you sampled there and there, there's definitely not enough data between because what you're doing is you're taking this point here and comparing it to this point here, and what's going to end up happening is you're going to get a straight line. That is not what happened. That is by far not what happened at all, as opposed to where you're right here and right here. If you draw a straight line there, that's basically exactly what happened between that point and that point. So what ends up what the caveat of that is that the control may not behave as expected. So that's a possibility when you're dealing with digital control logic. It could become a case where it doesn't react like you expect it to react. Um, so yes, be aware of that. So here's an easy way to figure out if it's going to be viable or not. Here's an easy way to figure it out. To evaluate if the sample rate is sufficient to directly use a controller compare FS, or the sample frequency, with the natural frequency. But with the natural damped or bandwidth of the system. So, as a good rule of thumb, if you have if the sample frequency is 10 times the natural frequency, we'll call FM, a continuous a continuous domain design is feasible. Um, Golly, man, this is a lot. So one of the things about a sampling function, like I'm trying to give you all the best version of the notes that I can. Like in order to check for this stuff, you basically have to discretize a signal. Um, and to do that, you have to use like your sampling time interval and the sample step and uh, a bunch of other stuff that's like it's like intuitive but not. Basically, if you're gonna do a sampling function, that's gonna look like it's gonna look like this. So F S of time minus lambda, and then that's gonna be when there's a one, um, S plus T equals lambda. When there's a zero, that's everything else. That basically just means that any time that T is not equal to um that T is not a multiple of like, or that this that T that time T, this small t is not equal to an n times another t, you're going to get f of s at that t value equals 0. Um, that ends up being a geometric function. If you've never learned of that, or if you're like in middle school or high school or something like that, walk up to your teacher and be like, oh, I watched this YouTuber. Kind of know what a geometric function is now. something slight. Now, the thing about geometric function is that it adds up to zero. It basically will add up to converge to zero. That was this class, right? I don't think we're doing Z transform in this exam. But that's what the discretizing helps you get to, lets you get to where you're going to do a Z transform. So if you want to, cheese and crackers. So for example, let's say we have S plus 5 over S plus 10 times 5. Well, then that equals Y. Well, multiply both sides and we end up having like S plus 5 SU plus 5U equals SY plus 10Y. And then we can discretize that. Y'all can't see it. We can discretize that by pulling out a YI everywhere we can. So we end up having a basically take a derivative of it, and you have 5 UI um plus UI minus UI minus 1 over delta t was the change in time. That equals yi minus yi minus 1 over delta t plus 10 yi. Then you pull out your UI and your yi. And you essentially get to write it out as yi equals 1 over 10 delta t plus 1 multiplied by yi minus 1 plus 5 delta t plus 1 plus ui minus 1. That's the difference equation. There's an example we can do here with actual values. I'm not doing that right now. Like I'm not going to do that. Because the last thing that I want to cover, because I'm also like, y'all got to remember, I've also been studying for like 2 hours. Like my brain is fried right now. Like I'm cooked. I'm cooked right now. Last thing I want to hit is the Z transform. I'm about to take a nap or something, bro. Like I'm exhausted. But I can't take a nap because I need to go to bed on time tonight. So if T is delta t, and that's our sample time interval. F of s, Fs of t, infinity, and then that's so if you have, oh geez, y'all can't see that. Look, I'm getting more like I'm losing it more and more a little bit. So we know that the big F of S equals the summation of k equals 0 to infinity of f of kt times z to the minus k. Um, oh, my bad. The z transform is the geometric series, not the other one. Um, so we might not cover too much of the z transform in the exam because like we didn't really go too in depth about it. Um, but the z transform comes from the step equate the difference equation. You got to get it into terms of I of ui and ui and yi. And you can z transform it in that way. There's a table, and I think that'll be the last thing I do unless I do an example. If y'all ask me for an example, I'll do an example. Um, but here's the table. So you got a step function. You got your Laplace. It's 1 over s. Your z is z over z minus 1. You have your ramp function. Laplace. It's 1 over s squared. Your z is tz over z minus 1 squared. And then you have your natural function. So that's e to the minus a t. Your Laplace is 1 over s plus a. Your z is z over z minus e to the minus at. Um, so yeah, let's just do a quick example, and I'm calling it for the day. Quick example. So you have you have y of s over, or you have y over s, and that equals like 1 over s plus 4. And this is the sampling interval. Step one, get into the difference equation, which ends up giving us 1 over 3 or 1 over 4. My bad. 1 over 4 yi minus 1 plus 1 over 4 ui. And that's yi equals that. Step two, you find the Z transform. So you break this into components. So 1 over 4 yi minus 1 times z plus 1 over 4 ui that's times z as well. So yz equals 1 over 4 z minus 1 times yz plus uz y over u, z on each side, z is 1 over 4 minus z minus 1, z to the minus 1. And that, my friends, it's pretty much all you need to know. Um, I'm calling it a night because I can't I can't cram for this. This isn't cramming. This is like literally working through problems and stuff like that. It'd be cramming if I was trying to memorize all this stuff before, but like a lot of the stuff I ended up actually knowing and remembering pretty well. So best advice for taking tests, all you students out there that subscribe to my channel and follow me, study, study a little bit in advance. Get a lot of rest before the exam. Like, take time, go rest, get some good sleep, eat some food, do something relaxing, get your mind off it. Don't cram like all night long. You're not gonna remember nothing. Um, but with that being said, I hope this was helpful. I really do. I really do hope this was helpful. I hope y'all understand this a little bit better. Like I said, I'm exhausted. I've been studying for like 2.5 hours. Um, so with that being, well, no, actually, I've been studying for almost 3 hours now that I think about it, because I started about like 5 o'clock or 5:15. But with that being said, I want to say thank you guys so much for watching this video and the stream. If you liked it, strike that like button like a ninja really would. Subscribe today to join the Shinobi. Good luck on your 462 exam. I'm sure you're going to do fine. It's going to come out. It's going to be all right, y'all. It's going to be all right. But yeah, hope y'all enjoyed watching me try and figure this stuff out, because um it helps me. It honestly helps me study. That's why I do it. But yeah, I might be back on a little bit later for those who are not into all the study stuff. Playing a game like while I relax and stuff. But yeah, that being said, thank you for watching. Tune in next time and good luck on your exam. And I'll see y'all in the next one. Have a good night.